Last time we were together, we did the work that it took to begin to recognize what equilibrium really is and what it isn't. One of the biggest misconceptions about equilibrium is that when you reach it, the amount of reactant you have is equal to the amount of product that you have. That is not equilibrium. It's not even close to equilibrium. So let's get that out of our heads. What we did recognize is that equilibrium is a special kind of state where the amount of product that you're producing at any given time is equal to the amount of product that is being depleted from the system or going back to form reactant. You could say that another way as well. The amount of reactant that is reacting or depleting from the system, turning into product, is equal to the amount of reactant being formed at a given time. So you did the work in class of figuring out how much reactant A and B we had in a given scenario. And what we found is that while those amounts might differ, there was a common ratio that existed between them. We looked at the moles of product formed at equilibrium over the moles of reactant that were present at equilibrium. And we got, in this particular case, a value of 3 to 1. That's the beginnings of what one might call an equilibrium constant. We're going to find a different way to calculate it here in a moment, but that ends up being important. We also recognize that depending on your initial starting position, you might end up at an equilibrium that's a little bit different positionally than another situation might have. So, what do I mean by that? I mean, if I look down here, I ended at a position where I had 2.5 moles of A and 7.5 moles of B, but later on, I did another equilibrium calculation, ended with 1.25 moles of A and 3.75 moles of B. Those are different positions, but they produce the exact same ratio of 3 to 1. It really just depends on how much reactant and product you start with. What are the initial conditions? Those can change the overall equilibrium position. So equilibrium constants are a little bit more complex than just looking at mole ratios. I want to introduce you to something called the law of mass action. This is an empirical law, which essentially means it was discovered in a lab setting and seen to be true no matter what conditions you kind of imposed on a reaction when it reached equilibrium. And we're going to kind of define that law based on this reaction that you see right here, where I have two reactants. Let me pick a different color. We'll call the reactants A and B, and the two products C and D. And the lowercase letters in front of them represent coefficients, numbers that would give you a balanced equation. So the law of mass action just states that something called the reaction quotient, which is always products divided by reactants, is equal to a constant when the system is at equilibrium. There's some special things that you need to understand about this law. Instead of using mole values, we're going to use molarity or concentration values. It's just easier to measure. And so when you see from now on something that looks like this, a bracketed substance, in this case, one of my products. That is referring to the concentration of C, not just C. So it really just means the moles per liter or molarity of that particular compound. And so you'll notice in the reaction quotient that we have here, we're multiplying, this is multiplying C times D, but first raising each to a power. And that power is the coefficient of that particular substance. We're then dividing it by our reactants concentrations multiplied together, but also raised to their individual coefficient. Very important that you do it that way. Well, long story short, it was noticed that if you did that at a particular temperature, and it is important that you keep the temperature the same throughout, that ratio gave you a number, and that number was called the equilibrium constant. And it did stay constant as long as things like temperature and pressure were also kept constant. So we're going to do something right here where we look at a few reactions and we set up what we would call an equilibrium expression. In and of itself, it's not all that useful, but we're going to find it's terribly useful when we look at reaction data. Okay, but first we just want to learn to set it up. First time through, we're going to look at homogeneous or homogeneous reactions, and when we say that, we're looking at the phase labels. So if you look, everything in that reaction is a gas. So if I said, draw me or write out the equilibrium expression for, part A up here, I'm going to look at my product concentration, CH4, multiplied by the other product, CO, and then divided by the reactant, in this case, C2H4O. This is called an equilibrium expression. Really simple to write. Let's do one more and we'll come back and maybe practice one as a class. In part B, you get a similar situation. It's always products over reactants. So we're always going to say, in this case, O3 divided by O2 concentration or molarity, but I have to raise each to the coefficient that is in front of the substance. Easy enough. Let's look at heterogeneous reactions because they're a little bit different. Long story short on this, you only want to include things in an equilibrium expression if they have concentrations that are readily manipulated or adjusted. So what does that actually mean? Well, it turns out the things that are susceptible to changes in concentration are gases and aqueous substances. All other things, solids and liquids, are not. So if you want the short answer on this, you only want to include substances in your equilibrium expression if they're a gas or if they're aqueous, and that's it. So if I look in this particular case at part A, all I'm going to do in part A is write K equal to my product, C4H10. I'm going to include its phase label because we don't want to get confused. I know we have C4H10 on the left side also as a liquid, but here I only include the gas. I only include the product. Let's look at, say, C. Same thing. I don't want to include solids, and so my equilibrium expression here is going to be CO2, a product, divided by CO, a reactant, and we leave out the Fe3O4, we leave out the FeO. No solids, no liquids ever in an equilibrium expression. Okay, we're going to come back to class right now and just practice a couple of these before going on to do some actual calculations. See you soon.